Thank you. Diego and Marco, and the floor are yours.
Okay, thank you. Uh, Good morning, everyone. Let me share my screen here. Here. So I guess you should be able to see it right now. Uh, okay, so hello, everyone. I am Diego Mendez. I am associate professor in Universidad Javeriana in Bogota, Colombia. I would like to use this opportunity today to talk a little bit about this indoor positioning systems initiative that we have right now that uses many of the advantages that TinyML has. And well, this initiative has been supported by the ICTP and Universidad Javeriana as well, and it's again under this big umbrella of the TinyML educational initiatives. In this project, I collaborate initially with Marco Zenado here also in this course, but also we have also other collaborations with master students, undergraduate students, some researchers and professors from our universities. I just realized, Marco, that we have 3 Italian professors in this initiative with such a good coincidence. So okay, so in this indoor positioning systems project is the result of the need of trying to track devices, things, even people in indoor environments. So, so what's the problem behind this? The problem is that when you have a typical outdoor localization problem, which has been widely studied and solutions are already mainly based in global navigation satellite systems like GPS, which is operated by the US. In these cases, and if you're in an outdoor scenario, it's quite simple. The solution you normally use the this trilateration approach, where if you have at least 3 to 4 signals received from this GPS constellation, you can estimate based on the received power from this signal your current position. Okay, so and in some other cases, this localization precision can be improved by integrating. Let me activate here the laser pointer here. Sometimes you can also improve this precision by integrating a non-static location that can send correction information in order to improve the accuracy of this estimation here. And this technique works pretty well. It has really low errors. I mean, in the orders of like a couple of meters, which is quite good for outdoor environments. But what's the case when you're in an indoor scenario? In these cases, GPS-based solutions suffer from what is called line of sight problem, which reduces its effectiveness when it's not possible to receive the signals of this GPS constellation. In So basically, because the GPS signals are not strong enough to penetrate the building structures, and hence the receiver is not able to capture these signals. So in conclusion, this type of solutions are not feasible for indoor environments. So then what we need now is we need to provide a new positioning infrastructure that is able to actually track this moving object. And I say object, but it can be an object attached to even a person. And then you just track the object, which at the end you're tracking people at the end. But that's the general problem. So you cannot use this kind of approach in an indoor environment. So then you just have this kind of like scenario now that now the object needs to be tracked by newly deployed infrastructure like what you have here, where we're going to have what we call a scanning station, these four red dots, and we want to know where this moving object in green actually is. But what's the problem? The problem is that you cannot use this estimation of distance based on the receive power of a radio frequency signal, because when this device transmit a packet, or in the other direction, when this scanning station transmit a packet, it's not received in a direct way, but it can, since there are obstacles and reflections, so the amount of power that is received is not necessarily what it's supposed to be using a line of sight approach. So you will have something like a reduced amount of power received by, for example, this scanning station, which, if you use this previous approach, will estimate in that this device is actually farther away than what it actually is. So, and that's going to happen in all of these signals. So that's why I have like these rounded arrows, because it's the signal is not actually arriving in a straight line kind of way. So what you have right now is an object here in green, some scanning stations that are actually receiving what we call receive signal strength indicator, is the amount, but basically a way to measure the amount of power received in basically any radio frequency communication. It can be Bluetooth, it can be Wi-Fi, and each of these scanning stations is receiving one particular value. Normally, they're all different because it depends actually on the whole scenario. And but with this information, it's impossible to apply trilateration. It's not going to be a good estimation of the position. But then what you know is that this combination of RSSI values, these four RSSI values in this particular case, is what is going to be a fingerprint of that specific location. If you move the object, the RSSI values are going to change as well. You're not going to be able to have like a closed mathematical form in order to estimate that value, the position with those values, but you know that the combination of those values is giving you a fingerprint of that location. And we know that the fingerprints are unique. That's why this technique is called fingerprinting. So having that in mind, then we go back, and then this is the scenario again. So who is going to be in charge of estimating this? But probably let me go back one step here. So if we have this fingerprinting scenario, okay, now we know that each location is going to have a particular fingerprint. So what we want to do now is to have a machine learning approach that is going to learn these fingerprints for each specific location, which is actually what we normally have like in a classification approach. You just have some values, and you're going to label that to that particular location, and then you're going to allow this learning algorithm to actually adjust the parameters of the model to be able to predict then with new values that specific location. So that's our approach. But then who's going to be in charge of estimating this? So imagine that we now have basically we can have two different approaches. In the first one, we have here in black the device that we want to track. This device is going to be sending broadcast packets in a periodic fashion, and this is going to be kind of like our first step. So all of these scanning stations are going to be listening to these broadcast packets, and with each packet that they receive, there's a corresponding RSSI value. But the problem is that this is a distributed infrastructure. So now we have to consolidate all of these values into one single point of centralization, if I can say that. in order to have now that fingerprint. We now have all 5 values, the one that is received by the scanning station 2, and all the other 4 received by the other scanning station. So now we have to consolidate that in order to have those 5 values that are going to create the fingerprint. And then after that, when you have all those values, then this scanning station is going to run the machine learning model in order to estimate where this black device is. So that's what we call intelligence at the edge infrastructure. So we need an infrastructure that is scanning for these packets and then consolidating the information and doing the inference process. Let me talk probably later about the advantages and disadvantages of each approach. So in the second approach, we have exactly the same scenario. We have a device that we want to track. We have an infrastructure. But then in this case, the scanning stations are actually not scanning right now, but they're actually broadcasting again packets in the same way that in the first scenario, the moving device was doing. But in this case, is the device, the moving device is actually listening and is receiving those packets. Look at the direction of the arrows are now going to be received here. The good thing now is that this device already has all 5 RSSI values, and then with that, then this device can actually run the machine learning model, and then it can actually know where it is. Okay, so in this case now is what we call intelligence at the mobile device. Okay, so there are many advantages and disadvantages for each of these approaches. In the first one, the problem is that you need an infrastructure. Right? You need to deploy an infrastructure that is it cannot be, you cannot just use the infrastructure that is available, for example, in a university campus, that you have so many Wi-Fi access points, right? Because that infrastructure needs to be modified in order to do this second and third step, to consolidate the information and then to run the machine learning model. So that's a big issue right there. But the good thing is that this device, the device that you want to track, needs to do just a minimum amount of work. You just broadcasting packets and that's it. And then you just know where it is. So you just need minimum requirements for this one. In the second approach, the good thing is that these packets, that you can normally receive on a radio frequency communication, are quite standard. So almost in each packet that you receive, even on a Wi-Fi communication, has this RSSI value. So you can probably use the already available infrastructure in a community or in a university, in many different scenarios, and then you just rely on the power of this device to actually run the model. So the good thing is that you can use the infrastructure, but the problem is that you need now more computational and probably storage capabilities on this mobile device, which is going to also impact the lifetime, because these devices are going to, of course, the black devices are going to be running on batteries in order to be mobile. So those are the different approaches for to define who's going to be in charge of calculating the position. So so we have actually when you have this even in any of these approaches, you can now have a different way to estimate this. So you can have a classification or a regression way to do it. So in the classification approach, you what you do is that you have a device, for example, located in position in location 4, and then you just have a label for that location. You say this is location 4, or this is label 4, whatever you want. Just collect information with the scanning station, and then you label that data, okay, with that particular position. And then you do that across the whole map and the whole place that you want to do. The good thing is that normally this approach has a really good accuracy, as you're going to see it later. But the problem is that this approach cannot estimate the location of the device in a position that you haven't acquired data before. It will only be able to classify each receive packet of RSSI values to one of the labels that you have previously defined. Okay, so you're not going to be able, you only classify to one of these 7 locations, but you cannot estimate the position in between of these positions. Okay, of these locations, I'm sorry. So that's one way to do it, and this is the first case study that we have. This is something that we did in a regular apartment. We have here kind of like 2 bedrooms, living room, a dining room, and kitchen, really standard apartment. So what we have here is that you see all these kind of like positions. You have 0, 0, 0, 1, 0, 2. So in these places are information was collected about this. So we had the device in a specific location transmitting to 5 different scanning stations, and then for each packet, then we have an RSSI value, exactly what we were talking before. So the way to do this is that we had to go around the whole map, collecting all this information, and then training a machine learning model. So the proposed solutions in terms of the architecture is we have some tags, the ones that are going to be moving around. This is going to be based on Bluetooth Low Energy. We use the CC2541 Texas Instrument transceiver that is normally included in these HM10 modules. Are going to be sending this information. We have the scanning stations that are based on ESP32 and an ESP82266. We had to use 2 because then we have a Bluetooth communication. Then the ones that are going to be consolidating this information to what we call the broker. This communication is based on Wi-Fi. So we have Bluetooth here, and then we have Wi-Fi here. And even though the ESP32 have these 2 communications, you can only use one of those at the same time. So that's why we put 2 of these so that we can have continuous Bluetooth communication and continuous Wi-Fi communication. And this broker, which is based on a Raspberry Pi, is not only, or this device is not only in charge of collecting the information, but also running the deep learning model. So what we have for the scanning stations, as I said, is the ESP32 and the ESP8266 to have a continuous Bluetooth and Wi-Fi communication. This is what we have here on the right picture. And we have a scanning intervals of around a little less than 5 seconds. We have an MQTT-based information in order to centralize everything. And these are battery power as the tag devices. As I said, they are based on the Texas Instruments CC2541. And these are just sending advertisement packets for Bluetooth. Okay, this is doing it in normally it's half a second. Every half a second, they're sending a packet. So this is what we have. We have the scanning stations. So the first thing that we need to do is, of course, I mean, I'm already telling you this and this works, but at the beginning, we need to first try to understand if this made sense, okay? So what we did at the beginning was we were running around with the device, moving into the bedroom 2. This is main bedroom. This is the night table, the desk. This is the yes, this is the television, the couch, the kitchen, and we're moving around, and we were trying to see if the signals that we were receiving kind of like made sense. So in this case, you see like a station 3 with the highest RSSI value, and then that was that corresponded to the room that is assigned to the lab. And then we have another bedroom, and then in this case is I think it's a scanning station 5, which is higher, and it corresponds to the bedroom. And then we saw that it kind of like made sense. So if you see that it kind of like made sense, you expect that this machine learning models to be able to actually figure out a good model with a good performance. Okay, so that's what we have here. We have some. This is kind of like having a proof of concepts before like running a big experiment. So again, we, as you have seen during this week, we use Edge Impulse to train a model and then to deploy it. But then at the beginning, since we had kind of like the idea was to have like 26 different locations, we started with just 3 in order to see again if this made sense. And then this is the good thing about this feature explorer that you have in Edge Impulse, that you can actually see that kind of like the features uh, seem to be separable. That you can actually separate those classes easily. So then in those cases, we move forward to a more complex scenario where we're going to have all 5 scanning stations. Then we have, this is kind of like the architecture of the neural network with we use these 7 features: the average, the minimum, the maximum, skewness, kurtosis, standard deviation, RMS, for each of the values collected by the scanning station. So if we have 5 scanning stations and 7 features per input, then we have 35 features, which are which defines the 35 neurons for the input layer. We have 2 hidden layers, and we have 26 uh, neurons on the output, 1 per location. Okay. Of course, we had to run some pre-processing. You can see the RSSI signals are quite noisy, so we just had like a moving average in order to like have like a smoother signals in order to feed this to the machine learning model, so that the machine learning model doesn't um, change that much, because again we're supposing that we're kind of like tracking objects like a wallet or your cell phone, your backpack, or even a person, which are not going to be moving really fast in the space. And in that case, you're going to assume that the RSSI signals should be kind of like stable and changing slowly in time. So that's why we applied this moving average at the beginning before fitting this into the neural network. You can see these are the features for all 26 locations, which now is a little uh, it's a little messy, but still, uh, with such a configuration of the neural network, we were able to have in the validation set an accuracy of 95, almost 95%, which is quite good. Um, I can say that. This is, of course, for just a couple of locations, because it's almost impossible to see for all 26 locations right there. You see the behavior of the ones that are properly classified and the ones that are not. And then when we deployed this, we had kind of like around 88 to 90% of accuracy when already deployed in the apartment. Okay, so let's think about this. I mean, what about some post processing? Okay, again, what we were seeing is that even when having the device just standing still, the the radio frequency signals are quite noisy because of like all of the other signal that are also in the same bands of this is 2.4 gigahertz, and you have many other devices on these frequencies, and also any kind of modification of the position, right, like that, are going to affect these values. Even obstruction made by yourself by holding the device is going to affect that. So, but again, these are not, we're assuming that these stacks, the things that we're kind of that we want to try, they're not going to be moving really fast in time. So, and then in this case, what we proposed was a moving median, not an average, but a median, because since we cannot have an average on labels, because having an average on labels doesn't make any sense. But we had a median in the case, in the sense that we had kind of like the last 10 locations that are that are the last 10 outputs of the machine learning model, and then we just organized that, and we had probably a way to say this is the most frequent one, because you can see, for example, a typical problem with this is that you, for example, see that the device is in position 1.0, 1.0. So sometimes it jumps to 1.1 and then go back to 1.0. That's, of course, some noise that you're getting into the device. But then if we apply a really simple moving median to the values, we move from 88% of accuracy to 94. This is on real deployments. Okay, so as a really simple post-processing can actually help a lot on these approaches. So that's kind of like a suggestion for you, so that you, depending on the application scenario, on how you're deploying the solution, you can twist a little bit, like fine tuning your solution in order to make it work a little better. Okay, so that's the case when we were having Bluetooth, and then we were having um, all the intelligence on the border, on the infrastructure. The device was really simple, and there was the infrastructure in charge of like calculating this. So the second scenario that I'm going to show you right here is what we did last year with Marco in the Marconi lab at the ICTP. And then in this case, we were considering now what is called channel state information, which is available for Wi-Fi communication. This is not available for Bluetooth. Bluetooth just, you can just have one channel and one RSSI value, but with Wi-Fi, you have 64 subcarriers, and for each one, you can have kind of like the equivalent to this RSSI value. Actually, you have like a real and imaginary part, and you can calculate the amplitude and the phase of these signals. But it's kind of like the same concept, but on different subcarriers. So you have like a richer, you have richer information in order to feed your machine learning model. So in this scenario, we had kind of like a similar approach with, we have this kind of like configuration. We had like a meeting room and the lab room. We had 9 positions here to collect information, and we had 16 in the lab room. We had only 3 access points, and there were actually different access points of different manufacturers. And then we had kind of like the same approach. We had the device, right? The device, but then in this case, the device is the one that is in charge of running the model. And then the first step is that you just need to run the channel state information request, and then all these access points are going to reply to the device with the channel state information values. And then the model is going to be run on the device. So this is the second approach that we had when I was explaining at the beginning. Just some information about what is called Wi-Fi sensing, which is based on channel state information, which is basically to kind of like understand the properties of the communication link. And it kind of like represents a combined effect of different effects, of different different effects, like scattering, fading, power decay with distance. And this is, since it's such a richer um, uh, um, such richer information when compared to RSSI, you can actually characterize in a better way the indoor scenario. Actually, this is really used for human activity recognition. They can actually understand, using Wi-Fi with channel state information, your activities. They can actually know if you're sleeping, if you're running, if you're walking. Actually, there's a really interesting work that we found with Marco last year, that they can actually, with a pretty decent accuracy, estimate what you're typing on your keyboard on the computer, and they can actually estimate, for example, the passcode of your bank information. So which is quite scary, but gives you like an idea of how rich this kind of information, how much information you have in this approach. So as I was saying before, you have 64 subcarriers, which gives you 64 real and 64 imaginary values. It's going to give you 128 values plus 3 RSSI values. And I'm sorry, no, 128 values plus 1 RSSI value. But since in our scenario we have 3 access points for each sample, which implies requesting and receiving 1 CSI packet per access point, now we have 128 times 3 plus 3 RSSI values, which gives us 387 values per sample. Of course, this is going to be more demanding for the device, for the machine learning model, because now we have kind of like a sample structure like this one. We have, for each access point, we are going to have 64 subcarriers. Each one is going to provide you with one real and one imaginary part, and then at the end you have all these values for just one simple case, for the single sample case. I'm sorry. But that's when you just capture one value. But the problem with this, as I said before, the radio frequency signals are quite noisy, and then sometimes you just have like a time series approach. You just don't have one sample, but you have a sampling period, and then what you define as a sample is just one of these, like 128, 128, 128 is going to be your one single sample, and then you have this over time to have a time series approach. Okay, like what you were like what you can do with this example that you have with our devices on activity recognition with the accelerometers. You just have like a 9-degree IMU. That's 9 signals per sample. This is 384 signals per sample. Okay, or 384 values per sample. Okay, so which is quite demanding. So what we have in this case is now we have 384 CSI values, and then we again have this average minimum maximum kurtosis skewness features, and then it's going to be input to the neural network. And then we're going to have, in this particular case, 25 output classes, one per location, similar as we did before. But then this is way more complex because it's a bigger neural network. So you can see this is what the impulse looks in Edge Impulse. Then you have all these input axes, 387, as I said, 384 plus 3 RSSI values. The good thing is that we separated the spectral analysis for just the channel state information values, and for the and an spectral analysis for the RSSI values. Why? Because we wanted to then compare how good the CSI is actually how good is behaving the solution based on CSI versus the performance based on RSSI. So that's what we had here, and then we had this result. These are many different solutions. This is just for one sample, and this is for 5 samples for the time series case and 10 samples for the time series case. A first conclusion is that the CSI is always better than RSSI. It's quite simple to see here, is that the green bars are always larger than the blue bars. It's as simple as that. Okay. Of course, it's way more complex. It's a heavier model, but it's always better. In any scenario, it's always better. And anyone can say, okay, that's kind of like obvious. Of course, it's obvious, but for some cases, the difference is not that much, but for some other, the difference is huge of the amount of accuracy that we can actually achieve with CSI. And it's actually more stable. As you can see, for RSSI value, sometimes you have a decent accuracy, for some others a really bad accuracy. For the same kind of like configuration, the same scenario, the same data that we collected in the Marconi lab. Someone can say, okay, but with one sample, you're gonna have a really decent accuracy. Why would you go for the 5 or 10 samples time series case? But in this case, it's actually good to be considered, because in these samples, they can be actually really they're not really robust to noisy environments. If the environment is changing a lot, when you have a time series, the time series can actually probably capture in a better way the actual location of the device, instead of like having that with just one simple value. For example, just take into consideration that if that sample was actually collected when someone was passing in front of the device, then it's going to have like a wrong estimation. But if the person passes, but then you get 10 samples, and then one sample is separated by 1 second, and you're going to have probably one sample that is bad, but the other ones are going to be good, and then the time series is going to probably have a better performance in those more dynamic scenarios. Okay, so that's why or those are the conclusions that you can get from these results. The last thing that we're actually doing, and this is going to be my last 2 slides, the last thing that we're actually doing right now is to evaluate the regression approach. So this looks quite similar to what I had before, but the difference here is that now we have the locations again. I'm also again collecting information for a specific location, but I'm not giving it a label, but just two continuous values, like the coordinate in the x-axis and the y-axis. Okay, so you can say, okay, this is location 5 meters in the x-axis and 10 meters in the y-axis, and so on. So at the end, what you want to have is actually a continuous function that is going to give you a continuous value as an output. Okay, so it's not going to give you a class, but a continuous value for x and y. And in those scenarios, is really interesting because then you can actually estimate the location of the device in locations in between. It can actually give you locations in between. Okay, so that's a different way to do it. And the good thing is that this is probably the most recent thing that we have actually done. The good thing is that we have now an error in meters. In the past, we just have an error in terms of like percentage of the amount of time that the inference is correct, or when it makes some mistakes. But in this case, you can actually it can actually give you points in between, right? These are the points that the blue ones are the point that where we collected values, and the green ones is where actually we tested the values. Okay, so you can actually test in positions where you didn't collect before, where you didn't collect data before, and it gives you an idea where you are. And these are kind of like we're actually working on what are the best models that we can actually use for this approach, and we have regressors like the linear decision trees, random forests, artificial neural networks, and so on. And this is what we're actually doing, and we want to see because at the end the problem of this approach um, or this kind of like solution is that you need to characterize the location or the scenario where you're going to deploy later. Okay, so I did this in an apartment. We did this with Marco in the Marconi lab, but that solution, that particular machine learning model, only works in that scenario. So I have one machine learning model for the Marconi lab and another machine learning model for the apartment. In another one for this was another apartment, and this is for the regression approach. Okay, so it's quite demanding to actually deploy these solutions. So it's better to have a regression approach, because then you can actually say, okay, how many locations do I have to collect data before training the model in order to have an acceptable error? Okay, because then you can actually estimate the locations in different places, and you can probably say, okay, if I have like 5 points where I collect data, then it's good enough for like the error that I want, the kind of like the spatial resolution that I want. So that's why we're working on this approach. And I did this. These are kind of like our the 4 papers that we have in this area. The first one, and you have all the QR codes if you guys want to check that. Probably you can actually later check that or with the DOI anyway. This first one is the first solution that we have based on Bluetooth, the one with the apartment. This second one is the extended version of this one where you have more details on the solution. The third one is the result that we have when comparing CSI versus RSSI. And the last one is just one book chapter. This is going to be out in the probably next couple of weeks for like this kind of like what I explained here, the machine learning techniques for indoor localization on edge devices. And I think that's it. I hope I didn't use more time than I was supposed to. Thank you very much. I don't know if there are questions. I guess they are.
Thanks a lot, Diego. No, we are very good in time. I think that you have in fact a few minutes, 5-10 minutes for some questions.
Okay.
Someone would like to have a question, a live question, or we can go directly to the message board. No? Okay. We have some questions here, Diego. I don't know if you saw. The first one, Jeremy asked about the possibility to how complicated should be to move from BLE, for example, or Wi-Fi to LoRa, for example, if you try to go for a bigger bigger areas like industrial, environmental, something like.
Actually, the whole concept is the same, right?
Okay.
The thing is that it's probably what I was concluding at the end. You still need to characterize the area. Probably with LoRa, since normally you have like um, an outdoor scenario, probably you can have a more general model, right? And probably you can kind of like characterize the LoRa with different with different stations, and probably you can have a more general model that you can actually use in different places. But still, it's the same idea. If we have different or access to different no, stations of LoRa, you can collect this, train the model, and so on. It's kind of like the same idea. Actually, one of our co-authors, Pietro had the idea or has the necessity of like tracking. I think it was cats, Marco.
Yep.
It was tracking cats on a forest, something like that.
Okay.
And that's kind of like the idea to use, for example, LoRa to do that. It's kind of like that. It's possible. It's the same concept, of course. Yeah.
Okay. Thank you. We have a question from Segun. Segun, you can open your mic or video.
Okay, thank you. That was very interesting. I'm just wondering, the two methods you try to use, the edge on the device. I'm wondering, did you try comparing the power consumption of both method to see which one is better? Because you said it has its advantages and disadvantages.
No, we haven't actually measured that. No, it will be interesting. The thing is that normally in those cases, you just focus more on like the power consumption of the device that you're just carrying around. Normally that's the case. Why? Because the scanning stations normally are plugged to the wall. And you can actually say they're normally on the, you don't care that much on the power consumption of that. But yeah, at the end, of course, you have to care about this because it's an environmental issue, right? Just power consumption of this solution. Yeah, we haven't done it, but we should. Yeah, we should. Normally, if I have to say something just based on what we have done before, probably the one on the edge device is cheaper in terms of like power consumption, because the other one you have many different devices listening, consuming information, normally additional information, additional power. I'm sorry, additional power, because these are devices that you have actually deployed. You have to put these new devices there in order to be scanning the information, scanning the radio frequency signals and consolidating information. These are not devices that have been deployed before, like what you have like with the Wi-Fi infrastructure. So probably in terms of energy, the second one with the device doing all the machine learning should be cheaper. That would be my guess. Yeah.
Thank you.
Thank you.
Diego, I have here a question from Javier Montoya.
Yeah, I'm reading.
You read here?
Yeah. Well, Javier says that since this is a 2D problem, how does the performance of the model changes if the number of available stations varies? Of course, I mean, it's going to affect, of course. If you have more access point, you're going to have more information and your estimation is going to be better. It's as simple as if, for example, you have one access point per room, for example, you're going to have a clean value for at least one access point, and the estimation is going to, of course, it's going to be better. The more access point you have a better spatial resolution. That's of course right. But we haven't characterized that. That's something that we, again, it's kind of like similar to my last conclusion about how many samples you need or how many locations you need to collect in order to have a decent resolution, and at the same time how many access points we need to have an acceptable. Yeah, but it's one of the things that we want to do, kind of like characterize this. Yeah. Thank you, Javier.
Thank you. There's another one from Emmanuel Davi here. It's about sensitivity. You saw?
Let me read it. Yeah. Have you measured the sensitivity of the system to external interference? For example, in big events like a soccer game, there will be a lot of people and devices streaming, sharing on social media, or this interface to the impact. We haven't, but the only thing that I can tell you, Emmanuel, is that we have actually collected information on normal scenarios. Okay, so with people moving around. So what we try to do is that when we have the device, when we're collecting the data, we don't keep it like in a clean way. We can try to move it around, like twisting it, having like obstacles while collecting the data that is going to be used to train the system. That will be kind of like my suggestion. I mean, you cannot, of course, I mean, it will be interesting to understand that. Of course, when you have a noisy environment, it's not going to work as well as that. But the good thing is it's good to have like data with noise. That's probably the suggestion. Yeah, but we haven't actually. It's quite difficult to understand how sensitive it is. But the thing that I can tell you that we have actually collected and we have actually deployed this on real scenarios. That's on a normal usage of a space. Yeah.
Okay. I see that you have a last one here from Arib. It's for you to explain how you captured CSI subcarriers from the Wi-Fi package.
This is quite a standard packet. Actually, on this ESP32, you already have support for CSI. So there's a special way to actually request this kind of packet. So you have a CSI request, and then the access point replies with that. Of course, you need to have the access point needs to support CSI. All access point don't have it, but I can tell you probably from the last 10 years, most of them they have it. So you can actually have that. There's actually one guy that is Hernandez is quite famous. You can actually check for channel state information Hernandez, and he has actually a toolbox that you can actually use with the ESP32 and I think also for your cell phone in order to collect the CSI values if you want to do it in.
I just published a link in the chat.
Okay, thank you, Marco.
Okay. More questions or no? Great presentations, Diego. And I mean, all your work with Marco and people from your university, from Javeriana and from ICTP. Congratulations. It's very challenging, very interesting.
What we want to do now is that this is what I was showing to Marco yesterday, that I finally have this have you seen this round screen for the SHAO? And we want to run this on the SHAO ESP32 on this screen so that you can actually see here kind of like where you are. That's kind of like to know where you are. Because one of the things that you have with this efforts is that you normally see all this kind of like in an offline fashion, and you just see all this on the terminal. So we want to have something really nice that as a watch, they can tell you where you are. But yeah, thank you very much. Thank you for your interest. You have all the information right there. If you can actually contact me if you want. Thank you very much. Thank you.
Thank you, Diego. Thank you, Marco.
Marcelo, for the invitation.